Hello everyone. So firstly, importing necessary libraries. The initial setup involves importing libraries crucial for data processing and manipulation. Datetime from Python's standard library is used for handling dates and times. The delta.tables module is imported for working with Delta Lake tables, which enhance the capabilities of Spark with ACID transactions and scalable metadata management. PySpark.sql.functions is imported to access a range of functions that facilitate various data transformations and queries. This includes functions for dealing with columns, conditions, and aggregations. PySpark.sql.types is used to define data types for data frame schemas. Configuring Spark SQL for Delta Lake. Several configurations are set up to optimize Delta Lake operations. The auto-merge property is enabled to automatically handle schema changes in Delta tables, which simplifies the process of adding new columns or modifying existing ones. Optimization settings such as auto-optimize write are configured to enhance write performance, and optimize.max file size is set to control the maximum size of files to be optimized. These settings collectively improve performance and manageability of Delta tables. Setting up Blob storage details. Blob storage details, including the account name, container name, and access key, are specified. This information is crucial for accessing and managing data stored in Azure Blob storage. The storage account name identifies the Azure storage account, the container name specifies the logical grouping of blobs, and the access key is used for authentication and authorization. Mounting Azure Blob storage. Azure Blob storage is mounted to the Databricks file system, DBFS, using the provided credentials. This step creates a persistent mount point, /mnt, that allows the code to read from and write to Azure Blob storage as if it were part of the local file system. The butils.fs.mount command establishes this connection, making it easier to interact with the stored data. Listing files in the mounted blob storage. The contents of the mounted blob storage are listed to confirm that the data has been successfully mounted. The dbutils.fs.ls command provides a view of the files and directories within the specified path. This step helps verify the availability and structure of the data in the blob storage. Reading file information. To proceed with data processing, the information about files within a specific folder, /mnt/dataset/ is retrieved. This involves listing the files and printing their paths to understand what files are available for further operations. Reading data from a CSV file. Data from a CSV file stored in the mounted blob storage is read into a Spark data frame. The file is read with headers and schema inference enabled. The data frame is then registered as a temporary SQL view, allowing SQL queries to be run against it. This process facilitates further data analysis and manipulation within the Databricks environment. Removing files or directories. Commands are provided to remove specific files or directories from the mounted storage. This is useful for cleaning up old or unnecessary data, especially when preparing for new data ingestion or storage operations. Dropping delta tables. Delta tables, which might be outdated or no longer needed, are dropped from the Databricks metastore. This operation ensures that any existing tables are removed before creating or updating new ones. It is a critical step to prevent conflicts and maintain a clean data environment. Creating delta tables with partitioning. A new delta table is created and registered in the metastore. This involves specifying the schema and partitioning the table by a column, example date. The table is created at a designated location in the mounted storage. This setup is necessary for organizing and optimizing data storage. Writing data to delta tables. Data from the data frame is written to the delta table using specified options. The data is saved in a format optimized for Delta Lake, with schema overwrite enabled to accommodate any schema changes. The data is also partitioned by the date column to improve query performance. Optimizing the delta table. An optimization command is run on the delta table to enhance query performance. This involves reorganizing the data and applying z-ordering by a specific column, example docid. This step helps improve the efficiency of data retrieval operations. Saving data to a single CSV file. Data is written to a CSV file format. Initially, the data might be saved in multiple files, but the goal is to consolidate it into a single CSV file. This step involves saving the data and later managing file output to ensure a single file output. Generating a single CSV file. A custom function is defined to handle the generation of a single CSV file from a data frame. This function writes the data frame to a temporary path, consolidates part files into a single file, and then cleans up temporary files. This process ensures that the final output is a single CSV file, which is often preferred for data export or sharing. Writing data to delta tables and querying. A delta table is defined and created or replaced in the metastore. The data frame is then written to this delta table location. Subsequently, SQL queries are executed to retrieve data from the table. If the table appears empty, it suggests removing existing data or resolving any issues before rerunning table creation and data insertion. Performing merge operations. Merge operations are conducted to synchronize data between source and target tables. The merge command compares records from a source table, or data frame, with a target delta table. It updates existing records if they match and inserts new records if they do not. This operation is essential for maintaining up-to-date data in delta tables. Unmounting blob storage. Finally, the mounted blob storage is unmounted from DBFS. This step cleans up the environment by removing the mount point, which is especially important when the data is no longer needed or when switching to different storage locations.